So today we're going to have a lesson in something called a point of inflection. So remember that in the previous videos we were looking at extreme values and critical points. So here we're going to be looking at something slightly different, but it's going to be kind of the same application of looking at a derivative, seeing where it's zero and if there's a sign change. But in the case of a minimum and a maximum, which were extreme values, where we really wanted to look where a first derivative was zero or undefined and had a sign change on either side of that zero value. For a point of inflection, we're going to want to look at when the second derivative is zero or undefined and changes sign. So because it represents a change in concavity of a function, I got a function right here that I just drew. This is going to be the function, we'll call it f of x. And just see really quick if you can identify, just maybe point out with your finger on the screen or something like that, points where we would have a change in concavity or a point of inflection. All right, so if you look at this, remember, concavity is, I like to use the metaphor a lot of the times, a concave up function is a smiley face, a concave down function is a frowny face. So where do we get transitions between a smiley face and a frowny face? Well, one of them looks like it's about right there. We have a smiley face up until that point, and then it switches to a frowny face. Then we have a transition that looks like right around here between a frowny face and a smiley face. We get another transition right about here between a smiley face and a frowny face. And then another transition somewhere around here between a frowny face and a smiley face. So if you look at all these points, it should be easy to see that in this case, let's use the color red to signify the second derivative. So red is the second derivative here. We have a positive second derivative, followed by a negative second derivative, a positive, a negative, and then a positive. So then at all these points in between, our second derivative is going to be zero at all those places we circled. And that's going to represent those changes in concavity or those points of inflection. So remember, we're not only looking where the second derivative is zero or undefined, we are also looking for where it changes sign. And in every single one of those points, the second derivative is not only zero, but it also changes sign. So let's look at a little bit more, let's say, mathematical approach to find these, where I'll actually give you a function and you can find the points of inflection based on what that function is. So let's just look at this problem. Give this problem a shot. I've given you a particular function, and try without a calculator. This is a perfect example of a non-calculator AP problem that you would be able to find the points of inflection for this particular function. Give it a shot. Pause the video. So if you've tried it out, well, the first thing you should do is points of inflection are related to a second derivative. So you should find a second derivative. But in order to find a second derivative, we have to find the first derivative. So in this case, you should have gotten that the first derivative would have been, this would be 1/4 x to the fourth minus 4/3 x squared plus 2x squared. All right? I'm sorry, this would be 4/3 x cubed, not x squared. Sorry about that. Okay, so now that we have this, we're going to need to find the second derivative. So we'll get in this case that f double prime of x is going to be x to the third. Then this will be minus 4x squared, then plus 4x, something like that, okay? So how can we rearrange this without a calculator to find out where this thing is zero? Again, think to factoring, okay? So what's a common term we have in here that we can pull out of every single term? Well, I would say we can pull an x out of everywhere, like that. And then let's factor it further. How can we factor x squared minus 4x plus 4? Well, that's just going to be x minus 2, the quantity squared. So therefore, with factoring, we've been able to come up with a very good representation of our second derivative here. And like I said, when you look at the AP problems on inflection points in the no calculator section, a lot of times you're going to have to be doing a lot of factoring to solve these ones. So now that we have our second derivative, if you were able to get to this point, continue watching the video. But if you got stumped here, try going from here to find those points of inflection. So pause the video. All right, if you're giving it a shot, hopefully you tried out kind of the same thing we did when looking for extreme values, where we look at a number line. So in this case, we want to find where the second derivative is going to be equal to 0. That's going to be at x equals 0. and at x equals 2. So we'll put those 2 points on our number line. And let's evaluate our second derivative. We know it's 0 there. Let's evaluate it to the right or the left of those points. So what's a number that's to the left of 0 that would be easy to evaluate that we can plug in? Well, I would say negative infinity would be a good one. So we'll have a negative infinity in this x portion, which is negative, times, well, anything squared is going to be positive. So the second derivative is going to be negative to the left of 0. What's an x value we could plug in between 0 and 2? Well, I would say x equals 1 would be good. If we plug in x equals 1, we're going to get a positive value. And then if we plug in, let's plug in something to the right of 2. Well, a good number for that would be positive infinity. If we do that, we are going to get another positive value. So where are our points of inflection? Our point of inflection will be right here at x is equal to 0, because that's where not only the second derivative was equal to 0, but we also had that sign change that when it switched from a negative concavity or a concave down function to a positive concavity or a concave up function. So let's go into Desmos and look at this particular function so we can kind of see how the math we did here translates over to Desmos, or over to a graph. So in this case, we got the red function is the original function, the green function is the derivative, and as we can see, we got everything correct. The second derivative was negative to the left of 0, and it was positive everywhere to the right with the exception of that value of 2 where it just touched 0 but it didn't cross it. And let's look at the graph. The graph is obviously concave down when we're to the left of 0, and it's concave up when we're to the right of 0. Notice there was no change in concavity. There was no change between a smiley face and a frowny face that went on at x equals 2. So therefore x equals 0 was our only point of inflection that we got for this particular function. All right, so let's try another example. Here, we're going to do something a little bit different. Now I've given you a second derivative. Pretend this is on the calculator portion of the AP exam. So if they gave you a second derivative like this, how would you find out where we would have a point of inflection on this? All right, try to solve it yourself. Pause the video. Okay, so if you give this a shot, if we come down here, let's go back to this graph. Let's hide all this stuff. Let's also erase all that ink we put on here. And notice that if you look at that left-hand kind of equation space we have here, I have this equation already up. And if we look at this equation, where is an inflection point going to be? Remember, this is an equation of the second derivative. So we're looking for where the second derivative is 0 or undefined and changes sign. Well, that looks like that's going to occur right about here and right about here. Now, if we wanted to, we could find these values. One of them is obviously 0. The other one is about 0.961, something like that. So if I highlight these 2 points right there, those are going to be our inflection points, okay? Because they're where the second derivative hits 0 and it changes sign. So that one was pretty easy. If you had a calculator, that one wouldn't have been too hard to solve, all right? So let's look at another example where we looked at a regular function, find the inflection points. We looked at a second derivative, find the inflection points. So now let's do something different. Let's look at a first derivative. Pretend this is the derivative of a function f of x. So this is the graph f prime of x. If that was the graph of a first derivative, pause the video, see if you can just trace with your finger and identify those points where we would have a point of inflection in our function f of x. All right, so if you gave it a shot, remember what we're looking for is the second derivative to be 0 and for there to be a sign change. Well, if the second derivative is 0 or undefined and a sign change. So where are the places where the second derivative is 0? Well, I would say that would occur right about here. So why is this a place where the second derivative is 0? Because remember, this is the graph of the first derivative, so the slope of the first derivative graph will give us the second derivative. We have a horizontal tangent right here, therefore that means that's a point where the second derivative is 0. I'd say the second derivative is also 0 right here, right here. It looks like there's 1 right here, and then there's a place where it's undefined right here. So those are going to be our points that we're going to check out. All right, and again, I'll use red ink to signify the sign of our second derivative. Well, our second derivative, again, is going to be the slope of our first derivative curve. So we have a positive second derivative, 0 second derivative, negative second derivative. Then at this point, it hits 0 again, goes back to being negative. we hit a 0 second derivative here, and it looks like actually, yeah, I'm sorry, no, we got that right. And then we got a positive second derivative here, 0 second derivative here. This one looks to be roughly positive. We have undefined right here. And then if this is a straight line, I would say this is, going to be like, it looks like it's a positive kind of, or I'm sorry, that's going to be negative, sorry. That's the slope of the line. So that's going to be a negative second derivative right there. Let's continue this line here. All right, so let's look at what we got right here. So if we investigate these, again, we're looking for the second derivative to be 0 and then experience a sign change, okay? And remember, what we're looking at here is we're looking at the slope of this line to give us what the second derivative is going to be. So at this point, right in here, we have a second derivative of 0, and we have a sign change on either side of that. So I'll circle this point. That point would be a point of inflection. Really, it would be this x value right here. I shouldn't have circled the y value. Sorry about that. So let me redraw this. And then get this in here. All right. So yeah, we got something like that. So there we go. We got a point of inflection right there. Now when we look at this one, we have a second derivative of negative, then it hits 0, and then it goes negative again. So the second derivative hits 0, but there was no sign change right there, so therefore that x value would not be a point of inflection. Likewise, we go from a negative slope of the first derivative to a 0 slope to a positive slope, so therefore this x value would be a point of inflection. The second derivative hits 0, and we get a sign change. Now if we go over here, our second derivative goes from positive to 0 to positive again. So therefore, this value would not be a point of inflection. And then in our final one, we go from positive to undefined to negative. So therefore, our second derivative hits undefined, and we have a sign change in between there. So in this case, this function would have 3 points of inflections. And it's important to realize why these 3 x values I circled are the inflection points, and the ones I did not circle would not be inflection points, okay? So remember, it's just like minimums and maximums. Just because you have a second derivative equal to 0 doesn't guarantee you have a point of inflection. However, at every point of inflection, your second derivative is either going to be 0 or it's going to be undefined. So come tomorrow ready with questions, and I will see you there.